Right, so we're going to be looking at exercise 1B in this further mechanics module. We're going to be looking at using conservation of momentum to try and work out problems. So conservation of momentum is basically the idea that whenever you have a collision, that momentum is conserved. So the total momentum before the collision of the bodies will equal the total momentum of the collision, the total momentum after the collision. So you don't lose any momentum. And that's the idea that we're going to be using to solve these problems here. So this very first question, you have a particle P of mass 2 kilograms. It's moving with a speed of 3 meters per second on a smooth horizontal plane. Particle Q of mass 3 kilograms, that rests on this same plane. Particle P then collides with Q, and after the collision, Q moves off with a speed of 7/3 meters per second. So first thing we're going to do is just draw a little diagram to kind of represent that so we can keep track of everything. So we have a particle P and we have a particle Q. Q is stationary, so 0 meters per second. Particle P was moving 3 meters per second towards Q. Had a mass of 2 kilograms. Q has a mass of 3 kilograms. And then Q moves off with a speed of 7/3. So it makes sense that it would move to the right in my diagram as it's struck by P. We don't know what P does afterwards. It could continue after striking it. Alternatively, it could come back after striking Q. And you just make a guess really. So I'm going to guess that it's going to just continue moving to the right towards Q in this case. I'm going to call that V. And the maths will help figure out whether we've chosen the right direction for that velocity V or whether we've chosen the wrong direction. So question A, we need to find the speed and direction of the motion of P after the collision. So we need to work out this V. So these are the before values, velocities, and these are the after velocities. So we're going to be using the fact that we know that the total momentum before a collision has to equal the total momentum after the collision. So total momentum before equals total momentum afterwards. Momentum is mass times velocity. I'm going to take right as positive, so that will affect the signs on velocities in questions. In this one here, all the velocities are moving right, so I'm not going to have too much of a problem. So the total momentum before, that's going to be 2 times 3 for P, plus the momentum of particle Q, which is going to be 3 times 0, has to equal the total momentum afterwards. So for P, that's going to be 2V, and then for Q, that's going to be an additional 3 lots of 7/3. So we just work this out. So we get 6 there, and then we get 2V plus 7 here. Just continue to work through. We get a value of V to be -1/2. So that means that we know that here, this value of V is -1/2. So we've been using V as moving towards Q, to the right in my diagram. So with it being a -1/2, that means that we guessed the wrong direction for V. In actual fact, particle P after the collision will be moving left with a velocity of 0.5 meters per second. So we can answer question A. The speed and direction of motion of P after the collision. So the direction of P, I'm not going to write down is moving left because it all depends on how you drew your diagram. And so the examiner doesn't know whether you drew your P on the left and your Q on the right or the other way round. And so what you'll need to do is say, if it's changed direction, then you say it's changed direction. Because originally, P was moving to the right, 3 meters per second. We now know it's actually going to move left with a velocity of 0.5. So we just say it's reversed. So direction of P, so after the collision, the direction of P is reversed. with a speed of 0.5 meters per second. And I mean, that was with taking right as positive. I'm just going to show you how left would also give you the same result. So if I take left as positive and I still look at the total momentum before equals the total momentum after. Total momentum before will be 2 times, and now it's going to be -3, because this 3 meters per second is going to the right, which is opposite to the positive, well, opposite to this moving left. I'm taking moving left as positive. So this will be -3 in my calculation. Now if I continue working through like that through the rest of the calculation, so let's pretend we don't know what V is. Here I've drawn V as moving right, so because I'm taking left as positive, that's going to be 2 times -V, and then adding 3 lots of -7/3. So you need to take great care with your signs. Working this out, we'd get a -6 here, -2V, take away 7, and then working through, we would still get that V is -1/2, which makes sense. I mean, you might be expecting, because this is going the opposite direction, you might be thinking, why is V still -1/2? Because our value of V equals -1/2 relates to the decision we made here. We made that decision that V is moving to the right, so here, this value of V is -1/2. And so we can clearly see it's moving to the right with a velocity of -1/2, which actually means it's moving left with a velocity of 0.5 meters per second. So do take great care with your signs, and always whatever value you end up with, take it and then put it back into your diagram to help you realize which direction the particle is actually moving in. Don't relate it to that there. As you can see here, we've got V equals -1/2, V equals -1/2. Doesn't relate to that. It relates to what you decided in your diagram. And that's how I'm going to be approaching all these questions. There is a different way of doing it, but that's how we're working through them in these questions. So let's get rid of that. And now have a go at tackling question B. So question B, I want you to find the magnitude of the impulse received by P in the collision. So because these two things are colliding, P will receive, well, Q's being struck by P, so Q will receive an impulse in that direction. And P will feel an equal and opposite impulse in that direction. Or rather, an equal impulse in the opposite direction. So that's what they both feel. Now, if I want to find the magnitude of the impulse received by P, then I'd probably want to look at P. The only problem with that is I'm going to be relying on a value of V that I've worked out previously. Because P and Q will both receive the same size of impulse, it would make more sense and be a good exam technique to look at the impulse of particle Q, because we have values that have been given to us. We don't have to rely upon something that we worked out previously. So we're going to look at Q. I'm going to take right as positive when looking at the impulse, which is the change in momentum. So just substituting everything in. Our velocities are going right on our diagram, so everything's going to stay positive. So we end up with an impulse of 7 meters per second. Now that was the impulse that Q received, so we're just going to write a little sentence to say the impulse that P received. So therefore, the impulse received by P is 7 Newton seconds. going to look at the next question. Give myself a bit of space there. So we have two particles, A and B, of masses 2 kilograms and 4 kilograms. They're moving towards each other in opposite directions along this same straight line on a smooth horizontal surface. They collide, and you're told the velocities, well, you're told the speeds before the collision, and then after the collision, you know that A is then moving in the opposite direction. Its direction is reversed, and its speed is 2 meters per second. So before we look at the question, we need to draw a diagram. So we have two masses, 2 kilograms and 4 kilograms. They move towards each other. Their speeds are 3 and 2. And after the collision, we know that A is reverses direction with a speed of 2 meters per second. All right, that's all the information we know. So this is before and this is after. We want to work out the speed and direction of motion of B after the collision. So the thing that we're missing from our diagram is what's happening to B. Is it, after it collides, does it continue moving left? Or does its direction also reverse and it bounces away from A? We don't know, and so you just take a guess really. You can try and take an educated guess if you like, but I'm going to just guess that it's moving left. I might be right, I might be wrong. The maths will tell us, just like it did with the previous question. So we're going to use conservation of momentum. So total momentum before will equal the total momentum afterwards. I'm going to take right as positive. So the total momentum before, we're going to have 2 times 3 plus 4 times negative 2. The total momentum afterwards, right being positive, will be 2 times negative 2 plus 4 times negative v. So we just tidy this up. And so we end up with v being -1/2 here. So again, like we did previously, what that means is we know that this value of v here is -1/2. And that was assuming that the velocity of B after the collision was moving left. We can now see that was wrong. If it has a velocity of -1/2 and we chose moving left, then in actual fact it's moving the opposite direction after the collision. It's in fact moving right with a speed of 0.5 meters per second. So to answer A, the speed and direction of motion of B, well, we know that the direction is reversed, so we're going to write that. So therefore, direction of B is reversed. And its speed, or with a speed, of 0.5 meters per second. So that was question A. Question B asks us to find the magnitude of the impulse given by A to B in the collision. So because these two things collide, particle B feels an impulse in that direction, particle A feels an equal and opposite impulse as well. So if we're going to work out the impulse given by A to B, we could work out the impulse of either because they're going to be the same. Good exam technique again would be to look at A because we have information given to us, whereas particle B relies on something we could have worked out incorrectly. So looking at A, I'm going to take right or left as positive. Just for fun, I'm going to take right as positive. So you can see what happens. So the mass there is 2. Final velocity would be -2 because I took right to be positive. Take away 2 times 3. So we end up with an impulse of -10 Newton seconds. So what we've done here is we've assumed the impulse is moving right, but we know in actual fact it's not moving. The direction of the impulse actually left, so which is why we end up with a -10 Newton seconds. Had I taken direction to be left, I would have ended up with a +10 Newton seconds. But it doesn't matter in answering this question because it asks for the magnitude. So we will then go, therefore, magnitude of the impulse on, so given by A to B. So the magnitude of the impulse on B is 10 Newton seconds. So that's that second example now complete. We have 2 more to run through. So we're going to have another not necessarily another collision here. So we have particles P and Q. Their masses are 8 and 2 kilograms respectively, but this time they're connected by a light extensible string. So let's just start drawing that. So that's going to be P, that's going to be Q. This one's 8 kilograms, the other is 2. They're connected by this inextensible string. Particles are at rest on a smooth horizontal plane with the string slack. Particle P is projected directly away from Q with speed 4 meters per second, then it says to find something. So lots of times you'll be tempted to do this because you're told they're initially at rest. And then it says particle P is projected away from Q with a speed of 4 meters per second. And you'll be left with this diagram, and then question A asks you to find the common speed of the particles after the string goes taut. And then you're thinking, well, how can they both have the same speed if I already kind of know that Q's going with 4? Then surely they're attached by a piece of string that the answer is just going to be 4 meters per second. But the problem is that we haven't drawn this diagram correctly. Our velocities aren't in the right place. So yes, initially these 2 particles are at rest, but the string is slack. We're going to start off the modelling from the moment the string is taut. And at that moment, that's when particle P is projected directly away from Q with 4 meters per second. And at that moment, right at the start, Q has a velocity of 0 meters per second. So this is the before velocities. And then after, we know that they'll both move with the same velocity because they're attached by this inextensible string. And so they're going to move, they'll both move left because P is moving left in my diagram. So we'll call that V. We'll call that V. They're both moving with the same velocity. So we need to find the common speed of these particles after the string goes taut. So we're going to be using conservation of momentum. Total momentum before equals total momentum afterwards. Whilst I normally take right to be positive, here it'd be sensible for everything going left to be positive because the velocities are all going left. So total momentum before will be 8 times 4 plus 2 times 0. Total momentum afterwards, 8v plus 2v. We work this through. we get a value of v to be 3.2 meters per second. So, therefore the speed is 3.2 meters per second. Then, question B. Find the magnitude of the impulse transmitted through the string when it goes taut. So, if I'm going to draw impulse on here, because I'm not colliding, I'm going to draw it slightly differently. So, Q is suddenly being pulled by P. So, it will feel an impulse that goes in that direction. Now, I'm not talking about the forces. Yes, it would feel a tension through the string, but I'm just talking about the impulse. The impulse will be left that it will receive, and P will feel an equal and opposite. It will feel a bit of a drag from Q, if you like, a bit of a pull from Q in order to try and get it moving. It will feel an impulse going right. So, question B, find the magnitude of the impulse transmitted through the string when it goes taut. All right, so it doesn't matter which impulse we're trying to work out. It's both the same, so I'm going to do it for Q. I'm going to look at Q. I'm going to take left as positive because it kind of makes sense to use the same direction of impulse that Q is feeling. It's feeling an impulse in the direction of left of my diagram. So that's going to be mv minus mu. So it's 2 times 3.2, take away 2 times 0. So we get an impulse of 6.4 Newton seconds. Okay, one final question. So here we have two particles, A and B, of mass 2 and 4 kilograms, move towards each other in opposite directions along the same straight line on a smooth horizontal surface. They collide. We know the velocities before, and you're then told the impulse due to the collision. It then asks us to find the velocity. So let's first of all draw a diagram. A and B, 2 and 4 kilograms, moving towards each other with speeds of 3 and 2. Don't know the velocities afterwards, but we are told that the impulse they both receive due to the collision 7 Newton seconds. So it'll feel an impulse going in that direction, and A will feel an impulse going in that direction from the collision. We don't know the velocities, so they could go, well, they could go in either direction. You could go like that. You could have that scenario. You could have them both going left. Completely up to you. The maths would sort it all out. So I am going to just assume they collide and then both go in opposite directions. So I'm going to call this velocity A. I'm going to call this velocity B. So here they won't necessarily move with the same velocity. The previous example they did because they were connected. So here they might be the same velocities, probably unlikely. But I'm calling one velocity A, the other one velocity B. So first thing you'll want to do is go the total momentum before equals total momentum afterwards. I'm going to take right as positive. And what some of you might notice or realise is that this is going to cause an equation with two unknowns. But this might be the first thing you write down. So as you tackle questions, I'm just going to kind of model through some of your thinking. This might be your first thought. So I'm just going to write this down. We'll see what we get. Total momentum before. So that's going to be 2 times 3 plus 4 times negative 2. Afterwards, we're going to have 2 times negative velocity of A, or that VA, plus 4 lots of VB. So I guess the problem here is we have an equation with 2 unknowns, so we don't really have enough information to work out either. But what we haven't used is the fact that we know that the impulse of each of these is 7 newtons per second. So we'll have a look at the impulse instead. So if you're ever unsure with collisions, I would say, first of all, use conservation momentum. Total momentum before equals total momentum afterwards. Generally speaking, that will solve most of your problems. If not, then use the impulse as well. And then you might be able to just solve by using simultaneous equations. And in this case, it ends up being that you don't have to use simultaneous equations because you could just rely on impulse being the change of momentum. So let's look at particle A, first of all. I'm going to take left as positive because we know that the impulse it feels is moving left in our diagram here. So that's going to be a positive 7 there. 2 times our final velocity for particle A. And a negative 3 here, because that's moving in the opposite direction to what we said was positive. So again, you just need to take great care with signs with these questions. It's very easy to make a slip with a sign. So we end up with this, and we end up working out that the velocity, the final velocity of A is going to be 0.5 meter per second. So we've worked that one out. I guess you have 2 options here now. You could take this, you could substitute it into there to work out the value of VB. Alternatively, you could then look at the impulse of particle B. So I'm going to do that as well. I'm going to take right as positive because I know the impulse is right. So it just makes a bit more sense to take it that direction. Because then I can just put in a positive 7. So then this is 4 times the velocity of B minus 4 times negative 2. So we end up with the velocity of B being negative 1/4. So we've worked out the velocities of these 2 particles. As you can see, it wasn't necessary to have this. As I said before, you could have worked that out, then substituted into there to work out VB. But I've just done it by looking at the impulse of both particles. So answering the question, because I got a little bit ahead of myself, the velocity of A after the collision, that was this working here. So velocity hasn't asked for speed this time, so you need to give the direction. So what does my answer mean? So velocity of 1/2. So I can just add it to my diagram to have a look and see what it means there. So it means that I guessed correctly which direction particle A was going to go after the collision. In our diagram here, it's going to move left, but I can't write left, of course. So what I can say is that the direction has reversed because it was moving right with 3 meters per second. We can see now it's moving left with a velocity of 0.5 meters per second. So particle A, we can say the direction has reversed with a speed of 0.5 meters per second. So particle A has reversed direction with a speed of 0.5 meters per second. Right, that's question A. Question B was to work out the velocity of B after the collision. So we just need to take this value, put it here, to really make sure we know what's happening. And now we just focus on that bit there. So we initially thought particle B is going to be moving to the right in our diagram. We can see that because we worked out the value of that velocity to be -1/4, we guessed incorrectly. It's actually moving left. So what's happened to B? Well, it was moving left originally on our diagram. We now know it's moving left after the collision. So the direction of particle B has not changed. So the velocity of B will be that it continues moving in the same direction with a speed of 1/4 meters per second. So particle B particle B's direction, how am I going to write it? Particle B has not changed direction. Anything that communicates that it hasn't changed direction is absolutely fine. So particle B has not changed direction and travels with a speed of 1/4, so 0.25 meters per second. And there you have it. So that you're now able to go and tackle some of the questions from exercise 1B. My biggest tip, I guess, is to first of all take care with your signs when you're substituting it into conservation of momentum or into using the impulse as a change of momentum. And then second tip, whatever value you get there, just go back and see how it relates to the arrow or the direction you chose for that within the diagram. Don't do it based on that one there. Always take it from there, put it there, and see what it means there. Right, best of luck with those questions.